The technician's hands trembled as he screwed the final component into place. It was a small metal cylinder, no larger than a soup can, filled with vacuum tubes and circuitry that represented 3 years of desperate innovation. Outside the munitions depot at RAF Dumchurch on the Kentish coast, the summer dawn of August 28, 1944, was already thick with humidity and the distant rumble of something that sounded like a motorcycle engine cutting out mid-flight. That sound had become the soundtrack of terror for southern England. The buzz bombs were coming again. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. Sergeant Technical Malcolm Hendricks of the United States Army Ordnance Department had installed more than 400 of these devices over the past 6 weeks, but today felt different. The intelligence reports suggested that the Luftwaffe was planning something massive, a saturation attack that would overwhelm the defensive gun belt surrounding London. What the Germans didn't know, what they couldn't possibly have discovered, despite their network of spies and informants, was that every anti-aircraft shell being loaded into British and American gun batteries that morning contained a technological marvel that would render their carefully planned assault almost completely ineffective. The device was called the VT Fuse, though most of the men handling them had no idea what those letters actually stood for. Variable time was the official designation, a deliberate misnomer designed to confuse enemy intelligence. The truth was far more revolutionary. Inside each fuse was a miniature radio transmitter and receiver that would detonate the shell at the precise moment it came within lethal range of its target. No more hoping that timed fuses would explode at exactly the right altitude. No more relying on direct hits against fast-moving targets. The VT fuse turned every anti-aircraft shell into a proximity weapon that would kill anything it passed near. The stakes were existential for the people of southern England. Since June 13th, when the first V-1 flying bomb had crashed into Grove Road in London's East End, killing 6 people and injuring 9 others, the German vengeance weapons had terrorized civilians with a psychological intensity that conventional bombing had never achieved. The V-1 was a pilotless aircraft, essentially a cruise missile before that term existed, powered by a pulse jet engine that produced the distinctive buzzing sound that gave it the nickname Doodleblug. When the engine cut out, everyone within earshot had approximately 15 seconds before a ton of high explosive detonated wherever the bomb happened to fall. By late August 1944, the Germans had launched more than 8,000 V-1s toward England. Roughly 2,400 had reached London, killing over 6,000 civilians and seriously injuring 17,000 more. The psychological damage was incalculable. Unlike conventional air raids that came with warning sirens and the possibility of shelter, the V-1s arrived at all hours with minimal warning. The constant stress of listening for that engine sound, then waiting to hear if it would cut out overhead or continue past toward some other unfortunate neighborhood, was breaking the morale of a population that had endured 4 years of total war. British Prime Minister Winston Churchill had privately confessed to his advisors that the V-weapon threat was the most serious challenge Britain faced in the summer of 1944. Potentially more dangerous than the Luftwaffe's conventional bombing campaigns during the Blitz. The V-1s required no pilots who could be shot down or captured. They consumed minimal fuel and could be mass-produced in underground factories immune to Allied bombing. Most critically, they struck without warning at all hours, making normal life impossible for millions of people in southeastern England. The Allied response had evolved through desperate improvisation into a sophisticated defensive system that represented the cutting edge of military technology. Fighter aircraft equipped with high-speed engines patrolled the channel, attempting to shoot down or tip over V-1s before they reached the coast. Barrage balloons with steel cables created aerial obstacles that could destroy the flying bombs. Most importantly, a belt of anti-aircraft batteries stretched across the North Downs, positioned to create a wall of explosive fire through which every V-1 would have to pass. Lieutenant Commander Roger Faulkner of the Royal Navy had been coordinating anti-aircraft defenses along the Dover coast for 7 weeks. His command post, carved into the white chalk cliffs overlooking the channel, contained radar screens, radio equipment, and plotting tables that tracked every V-1 launch from German positions in the Pas-de-Calais. Faulkner's crews operated a mixture of British and American anti-aircraft guns, primarily the American 90mm M1 and the British 3.7-inch QF guns, both capable of firing 20 rounds per minute to altitudes exceeding 20,000 feet. The challenge that had frustrated Faulkner at every other anti-aircraft commander was the fundamental difficulty of hitting a fast-moving target at high altitude with shells that required precise timing to explode at the correct moment. Traditional anti-aircraft fuses were essentially small clockwork mechanisms that began counting down the moment the shell was fired. Gun crews had to calculate the target's altitude, speed, and trajectory, then set the fuse to explode at exactly the right moment. Even with radar assistance and mechanical computing devices, the hit rate rarely exceeded 5%. Most anti-aircraft shells exploded harmlessly in empty air while their targets flew past untouched. The VT fuse eliminated this fundamental problem through elegant simplicity. A miniature radio transmitter in the nose of each shell broadcast a continuous signal. When that signal reflected back from a nearby object with sufficient strength, the receiver triggered the detonator. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now, back to the story. The shell would explode whenever it came within approximately 70 feet of any metal object, creating a sphere of lethal fragments that made evasion almost impossible. The technological challenge had been miniaturizing radio components to survive the enormous acceleration forces when an artillery shell was fired, forces that could exceed 20,000 times Earth's gravity. Dr. Harold Ziegler of Johns Hopkins University Applied Physics Laboratory had led the development team that solved this seemingly impossible engineering challenge. Ziegler was a physicist who had spent his career studying vacuum tube behavior, never imagining that his academic research would become critical to national survival. The breakthrough had come from recognizing that conventional vacuum tubes could be redesigned to withstand extreme acceleration if every component was ruggedized and secured against mechanical failure. The team had tested hundreds of prototype designs, firing them from artillery pieces and recovering the fragments to understand failure modes. The development program had consumed 3 years and cost more than $30 million, a staggering sum for a weapons project in the early 1940s. The manufacturing challenge was equally daunting. Each VT fuse required hand assembly of dozens of miniature components by skilled technicians working under magnification. Quality control was absolute. Every single fuse was tested before leaving the factory because a premature detonation could kill the gun crew handling it. By August 1944, American factories were producing more than 40,000 VT fuses daily, a manufacturing achievement that rivaled the Manhattan Project in complexity and secrecy. Security surrounding the VT fuse program was obsessive. Workers in the factories knew only their specific assembly task and had no understanding of what they were building. Military personnel handling the fuses were told only that they were experimental weapons requiring special care. Most critically, the fuses were initially restricted to use over water or in situations where the enemy could not recover unexploded examples for study. The technology was so valuable that Allied commanders feared its compromise more than they feared losing battles. Across the English Channel, Oberst Heinrich Marquardt of the Flak Regiment 155W was preparing his crews for the largest V-1 launch operation attempted since the campaign began. From his command bunker near Abbeville in occupied France, Marquardt controlled 55 launch sites scattered across the Pas-de-Calais region. Each site consisted of a concrete launch ramp aligned toward London with storage facilities for the flying bombs and support equipment for the launch crews. Intelligence reports suggested that British anti-aircraft defenses had become more effective in recent weeks, but Marquardt had been assured by Luftwaffe headquarters that overwhelming numbers would saturate the defenses and ensure sufficient bombs reached London to achieve strategic effect.
The German military had invested enormous resources in the V-weapon program, seeing it as a potential war-winning technology that could force Britain to negotiate peace, even as Allied armies advanced across France following the Normandy invasion. Hitler himself had taken personal interest in the V-1 program, demanding increased production and more aggressive launch schedules. The psychological impact on British morale was considered more important than the actual physical damage, though the casualties and destruction were certainly significant. What Marquardt and his superiors at Luftwaffe headquarters could not know was that their carefully planned saturation attack was about to encounter a defensive technology that would render their numerical superiority almost meaningless. The Germans had observed increased anti-aircraft fire and improved hit rates, but they attributed this to better radar and fire control systems. The concept of a proximity fuse that could turn every shell into a guaranteed near miss was beyond their technological imagination. German scientists had investigated similar concepts, but concluded that the engineering challenges were insurmountable given the state of miniaturization technology in the early 1940s. The morning of August 28th began with routine preparations at anti-aircraft battery positions across southeastern England. At gunsight Baker 17, positioned on the North Downs near Ashford, Captain James Millworth of the United States Army Coast Artillery Corps was conducting final inspections of his 4 90mm guns. Millworth was a West Point graduate who had trained in the New Mexico desert, never imagining he would spend the war defending English villages against robot bombs launched from France. His battery had been in action for 6 weeks, firing an average of 300 rounds daily at V-1s that crossed their engagement zone. The gun crews were a mixture of American artillerymen and British auxiliary personnel working together with the practiced efficiency that came from constant action. Each gun required an 11-man crew to operate at maximum rate of fire. The loader rammed 40-pound shells into the breech, while the gunner tracked targets using mechanical sights linked to radar systems. Fire control officers in a nearby bunker calculated firing solutions using analog computers that processed radar data and predicted where the target would be when the shell arrived. The entire system represented the pinnacle of mechanical fire control technology, but it was fundamentally limited by the imprecision of timed fuses. Millworth had been briefed 3 days earlier about the new fuses his battery would be receiving. The briefing officer, a colonel from Ordnance Command, whose name Millworth never learned, had emphasized 2 critical points. First, the new fuses were absolutely secret and could not be discussed with anyone outside authorized personnel. Second, early test results suggested hit rates that seemed almost impossible. Millworth, who had spent 6 weeks watching most of his shells explode harmlessly while V-1s continued toward London, found the colonel's claims difficult to believe. Artillery had always been about volume of fire and probability. The idea that technology could fundamentally change this ancient equation seemed too good to be true. The delivery trucks arrived at 4:30, earlier than Millworth expected. Military police and armored cars escorted the convoy, and the drivers carried sidearms along with paperwork that required Millworth's personal signature.
The wooden crates containing the VT fuses were marked only with cryptic codes that revealed nothing about their contents. Millworth's crew began the careful process of unloading and storing the fuses in a sandbagged magazine that had been constructed specifically for this purpose. Each fuse was individually packed in foam padding with detailed handling instructions that emphasized the need to avoid dropping or jarring the devices. Sergeant Thomas McKinley, Millworth's senior gunner, examined one of the new fuses with professional curiosity. McKinley had been firing artillery since North Africa and had seen enough combat to trust his equipment while remaining skeptical of miracle weapons. The VT fuse looked heavier than the standard mechanical fuses they had been using, with a distinctive bulbous nose that housed the radio components. The base contained battery cells that would power the device during flight. McKinley noted the careful craftsmanship evident in the assembly, suggesting expensive manufacturing processes. Whatever this thing was supposed to do, someone had invested serious resources in building it. Across the defensive belt, similar deliveries were taking place at every anti-aircraft position. The logistics of distributing thousands of these classified weapons to dozens of battery positions while maintaining absolute secrecy represented a formidable challenge. Convoy routes were classified, delivery times were staggered to avoid creating patterns that German reconnaissance might detect.
Most critically, the fuses would not be used in combat until sufficient quantities were available to equip every gun in the defensive system simultaneously. The first combat use needed to be overwhelming and decisive, giving the Germans no opportunity to understand what was happening before the technology demonstrated its full capability. At RAF Dymchurch, Malcolm Hendricks completed his final inspection of the fuse assembly facilities and signed off on quality control reports that cleared another 200 devices for combat use. Hendricks had been working on VT fuse production and distribution for 8 months, ever since his electronics expertise caught the attention of an Ordnance Department talent scout who was desperate for technicians who understood radio theory. The work was exhausting and stressful, with absolute standards that tolerated no errors, but Hendricks understood the strategic importance of what they were accomplishing. The psychological burden of keeping the secret was considerable. Hendricks had watched V-1s pass overhead, their pulse jet engines droning toward London where his sister lived with her 2 young children. He had stood in the ruins of buildings destroyed by the flying bombs, helping to pull survivors from collapsed structures, while knowing that he possessed technology that could stop this terror, but was forbidden to use it until the strategic moment was right. The discipline required to maintain operational security while people died was perhaps the most difficult challenge any of the VT fuse personnel faced. Intelligence reports reaching Allied headquarters suggested that German launch activity was increasing. Aerial reconnaissance showed increased activity at launch sites throughout the Pas-de-Calais. Radio intercepts indicated preparations for a major operation, though German communication security prevented precise details from being determined. Allied commanders made the decision that had been delayed for weeks. The VT fuses would be committed to combat on August 28, 1944. Every anti-aircraft battery in southeastern England would engage with the new technology, creating a defensive barrier that would demonstrate the full capability of proximity-fused ammunition against the V-1 threat. The decision to commit the VT fuses required approval from the highest levels of Allied command. General Dwight Eisenhower, Supreme Commander of Allied forces in Europe, personally authorized their use after consultation with Winston Churchill and the combined Chiefs of Staff. The risk of technological compromise was weighed against the necessity of defending British cities and maintaining civilian morale. The advancing Allied armies in France were approaching the V-1 launch sites, suggesting that German possession of the technology would be temporary, even if they managed to recover and study unexploded examples. Most importantly, the psychological and physical toll of the V-weapon campaign had reached a point where any weapon that could reduce casualties was worth the risk of eventual compromise. At 0600 hours, Captain Millworth assembled his gun crews for the final briefing before combat operations began. The men gathered in the sandbagged command bunker, their faces showing the exhaustion that came from 6 weeks of continuous operations. Millworth explained that they would be using new fuses that required no timing adjustments. The fire control computers would calculate aiming solutions, but the shells would automatically detonate when they approached the target. He emphasized that hit rates were expected to improve dramatically, but maintained the security restrictions that prevented him from explaining exactly how the new fuses worked. The gun crews received this information with cautious optimism. Artillerymen learned early in their careers that new weapons rarely performed as advertised under combat conditions. The gap between testing range performance and battlefield reality had disappointed soldiers throughout military history. Still, the prospect of improved effectiveness against the V-1 threat was welcome. Every man in the battery had watched flying bombs pass through their fire unscathed, continuing toward London where each one would kill or injure civilians. The frustration of firing hundreds of rounds with minimal results had worn down morale more effectively than any amount of enemy action. The morning stretched into routine patrol as radar operators monitored the channel approaches for any sign of incoming V-1s.
The defensive system had become highly organized through weeks of continuous operation. Coastal radar stations detected launches from French territory and tracked the flying bombs as they crossed the channel. Fighter aircraft from multiple squadrons maintained standing patrols, attempting to intercept V-1s before they reached the gunbelt. The anti-aircraft batteries formed the final defensive layer, creating a zone of fire through which every V-1 had to pass before reaching London. At 0847 hours, the first radar contact of the day appeared on tracking screens. A single V-1 had been launched from positions near Calais, following the standard trajectory across the Channel toward the Kentish coast. Fighter controllers vectored a Hawker Tempest toward the intercept, but the V-1's speed of nearly 400 miles per hour made aircraft interception challenging. The flying bomb crossed the coast at Dymchurch, climbing to approximately 3,000 feet as it headed inland toward London. Every anti-aircraft battery along its projected track received firing coordinates and prepared to engage. Captain Millworth's battery acquired the target at 6 miles range. Fire control officers calculated the intercept solution and relayed aiming data to the gun crews. 4 90mm guns swung toward the designated bearing, their long barrels elevating to the calculated angle. Millworth gave the engagement order, and all 4 guns fired in rapid succession. The shells, each carrying a VT fuse, streaked upward toward the approaching V-1. McKinley watched through binoculars as the first shell exploded in a bright flash approximately 50 yards from the target. The second shell detonated even closer. The third shell's proximity fuse triggered at optimal range, creating a cloud of fragments that enveloped the flying bomb. The V-1 seemed to stagger in midair as dozens of steel fragments tore through its thin aluminum skin. The pulse jet engine cut out immediately as fuel lines were severed and control surfaces damaged. The flying bomb nosed over and began falling toward the rural countryside below, exploding in an open field 2 miles short of any inhabited structures. From launch to destruction, the entire engagement had lasted less than 45 seconds. Millworth's battery had just achieved what 6 weeks of conventional fire had rarely accomplished: a clean kill against a V-1 target with minimal expenditure of ammunition. The implications were immediately apparent to every man who had witnessed the engagement. McKinley lowered his binoculars and looked at Millworth with an expression that mixed disbelief with dawning comprehension. Whatever these new fuses were, they had just transformed anti-aircraft fire from a game of probability into something approaching certainty. The colonel's impossible claims suddenly seemed entirely credible. If this performance could be sustained across multiple engagements, the V-1 threat had just become manageable in ways that would have seemed like fantasy only hours earlier. What no one at Gunsight Baker 17 could know was that their successful engagement was being replicated across the entire defensive belt as more V-1s began appearing on radar screens. The German saturation attack that Oberst Marquardt had planned was about to encounter defensive technology that would turn his carefully calculated numerical advantage into a catastrophic failure. The morning of August 28, 1944, was about to become the day when the balance of technological warfare shifted decisively in favor of the defenders, and the German vengeance weapon campaign began its terminal decline into strategic irrelevance. The radar screens at Air Defense Command headquarters in Uxbridge began displaying what operators initially thought was a malfunction. At 0915 hours, multiple contacts appeared simultaneously across a 20-mile front stretching from Dover to Dungeness. Within 3 minutes, the number of tracked V-1s had increased to 17, then 32, then 54. This was not the typical pattern of sporadic launches that defenders had grown accustomed to over the previous weeks. This was the saturation attack that intelligence had warned about, a coordinated launch designed to overwhelm defensive systems through sheer numbers. Wing Commander Arthur Pembleton, coordinating air defense operations from the Underground Command Center, watched the plot board with growing concern. Fighter squadrons were already airborne and moving to intercept positions, but the sheer number of incoming targets exceeded anything the defensive system had faced previously. Radio channels crackled with reports from coastal observation posts as the distinctive buzz of pulse jet engines began echoing across the channel. Pembleton picked up the direct telephone line to Anti-Aircraft Command and delivered the engagement authorization that every gun battery had been waiting for since dawn.
At launch site Rotenburg 7 near Abbeville, Feldwebel Kurt Dietrich watched the 53rd V-1 of the morning roar down the launch ramp and climb into the morning sky. Dietrich had been launching flying bombs for 9 weeks, working with mechanical precision that had become almost meditative through constant repetition. The procedure was identical every time. Roll the V-1 from its storage building, perform final checks of the guidance system and fuel load, position it on the launch ramp, connect the steam catapult system that would accelerate the flying bomb to flying speed, then fire. The entire process required 18 minutes from storage to launch, and Dietrich's crew had reduced that time through practice to just under 14 minutes. The launch ramps were engineering marvels in their own right, massive concrete structures aligned with absolute precision toward London, 163 kilometers to the northwest.
The V-1's primitive autopilot could only maintain a heading and countdown distance using a small propeller that measured airflow. Launch alignment determined where the weapon would eventually fall, and German engineers had calculated those alignments with obsessive accuracy. Dietrich had no illusions about what his work accomplished. Each V-1 carried an 850-kilogram warhead that would detonate in a residential neighborhood, killing civilians who had no connection to military operations. The moral burden of this work was something Dietrich tried not to think about during the mechanical routine of launch operations. What Dietrich could not have known as he prepared the 54th V-1 for launch was that his carefully timed saturation attack was encountering defensive technology that rendered numerical superiority almost meaningless. The flying bombs that had been launched over the previous 40 minutes were being systematically destroyed by anti-aircraft fire that achieved hit rates exceeding 90%. The attack that Oberst Marquardt had planned as an overwhelming assault was becoming a mass execution of unmanned aircraft that never reached their intended targets. At Gunsight Charlie 9 near Hastings, 2nd Lieutenant Patricia Holsworth of the Auxiliary Territorial Service was plotting target tracks with practiced efficiency. Holsworth was one of hundreds of women serving in anti-aircraft batteries throughout Britain, performing every task except actually firing the guns. Her plotting table showed 8 V-1s approaching her sector simultaneously, their tracks converging toward the narrow corridor where her battery's 4 guns could engage effectively. The fire control officer, a Canadian captain named Morrison, was calling out engagement priorities in rapid succession as radar operators fed him updated target positions. The guns began firing before Holsworth could complete her plot of the 3rd target. The distinctive crack of 90mm guns firing in rapid sequence created a sound that had become the constant background noise of life along the defensive belt. What was different this morning was the immediate result. Holsworth watched through the observation slit as the first target simply disintegrated in midair, followed seconds later by the 2nd, then the 3rd. The 4th V-1 tried to maneuver, its autopilot making small course corrections in response to turbulence, but a proximity-fused shell detonated close enough to shred its control surfaces. The flying bomb entered an uncontrolled dive and impacted in the channel, raising a column of water visible from the coastal cliffs. Morrison stopped calling targets and stared at the plotting table where Holsworth had marked 4 destroyed V-1s in less than 90 seconds. His battery had been engaging flying bombs for 7 weeks with conventional ammunition, typically expending 40 to 60 rounds per kill when they achieved kills at all. They had just destroyed 4 targets with 11 shells, a ratio that seemed to violate everything he understood about anti-aircraft fire. Morrison looked at Holsworth and saw his own disbelief reflected in her expression. Something fundamental had changed in the mathematics of aerial defense, and neither of them fully understood what they were witnessing. High above the channel, Squadron Leader David Thornton of 501 Squadron RAF was pursuing a V-1 at maximum speed in his Hawker Tempest fighter. Thornton had developed specialized techniques for V-1 interception over weeks of constant patrols, learning to approach from behind and slightly below to avoid the weapon's explosive blast when it was destroyed. The standard technique was to fire cannon rounds into the pulse jet engine, causing fuel system failures that would send the flying bomb into the sea. The more dramatic technique, reserved for pilots with exceptional skill and steady nerves, was to fly alongside the V-1 and use the fighter's wingtip to flip the flying bomb's wing, tumbling it out of control. Thornton was lining up for a cannon attack when the V-1 ahead of him suddenly exploded in a massive fireball. No shells had been visible approaching the target. No other aircraft were in the vicinity. The flying bomb had simply detonated in midair, as though struck by an invisible hammer. Thornton pulled up sharply to avoid the debris cloud, momentarily confused about what had just happened. His radio crackled with similar reports from other pilots in the patrol. V-1s were being destroyed before fighters could intercept them, knocked down by anti-aircraft fire that seemed impossibly accurate. The realization spreading through the fighter squadrons was that their role in the defensive system had just become secondary. For weeks, fighter pilots had been the primary defense against V-1s, risking their lives in dangerous low-altitude pursuits of targets that could explode without warning. The psychological toll of this work had been considerable, with pilots developing nervous conditions from the constant stress of flying at maximum speed just meters away from explosive devices. If the anti-aircraft batteries could achieve the kind of effectiveness Thornton was witnessing, fighter interception would become unnecessary except in cases where flying bombs evaded the gun belt entirely. At Air Defense Command Headquarters, Wing Commander Pembleton was receiving situation reports that contradicted decades of accepted wisdom about anti-aircraft effectiveness. Gun batteries across the defensive belt were reporting kill rates exceeding 80%. Targets were being destroyed with average ammunition expenditure of less than 4 rounds per kill. The saturation attack that should have overwhelmed the defensive system was instead being systematically annihilated with minimal stress on ammunition supplies or gun crew fatigue. Pembleton drafted an immediate situation report for higher headquarters, knowing that the implications extended beyond the tactical success of a single morning's defensive operations. The strategic consequences were immediately apparent to senior commanders monitoring the engagement from various headquarters throughout southern England. If proximity fuses could sustain this level of effectiveness, the V-1 threat had been effectively neutralized.
German launch operations could continue, but the weapons would be destroyed in such high percentages that civilian casualties would drop dramatically. More importantly, the defensive resources currently dedicated to V-1 interception could be redirected to other priorities. Fighter squadrons could return to offensive operations over the continent. Anti-aircraft batteries could be repositioned to defend advancing ground forces or protect critical supply lines. Oberst Marquardt received his first indication that something had gone catastrophically wrong when observation posts near Calais reported massive explosions visible over the English coast. Initial reports suggested that V-1s were detonating prematurely, possibly due to mechanical failures in the guidance systems or propulsion units. Marquardt ordered an immediate investigation, but the flood of similar reports from multiple observation posts made mechanical failure seem implausible. Flying bombs from different production facilities launched from different sites were all failing in similar ways over the same general area. The only common factor was proximity to the British defensive gun belt. The possibility that British anti-aircraft defenses had achieved a breakthrough in effectiveness was difficult for Marquardt to accept. German intelligence assessments had consistently rated British anti-aircraft fire as ineffective against fast-moving aerial targets. The V-1's speed and small size were supposed to make it extremely difficult to hit with conventional artillery fire. Marquardt had planned his saturation attack based on calculations that assumed no more than 15% of launched V-1s would be destroyed by anti-aircraft fire. The actual loss rate was approaching 90%, a ratio that rendered the entire V-weapon campaign strategically ineffective. At launch site Heidelberg 14, Unteroffizier Franz Weber was preparing another V-1 for launch when the order came through to suspend operations pending investigation of the unprecedented loss rates. Weber and his crew had launched 11 flying bombs that morning, working with mechanical efficiency that had become routine. The order to stop was unexpected and deeply frustrating. German military culture emphasized following orders without question, but Weber could not help wondering what was happening over England that warranted suspending operations in the middle of a planned saturation attack. The psychological impact on German launch crews was significant. They had been told that the V-weapons represented advanced technology that would force Britain to negotiate peace. The propaganda emphasized German technical superiority and the inevitability of victory through advanced weapons.
The reality that British defenses had somehow neutralized this supposedly unstoppable weapon created cognitive dissonance that undermined confidence in leadership assessments. If the V-1 could be defeated so decisively, what did that mean for other German claims about secret weapons and advanced technology? Back at Gunside Baker 17, Captain Millworth's battery had engaged 14 V-1s over a 3-hour period and achieved 13 confirmed kills. The single V-1 that escaped destruction had suffered sufficient damage that it crashed short of London in rural Kent, causing no casualties. Ammunition expenditure totaled 53 rounds, an average of just over 4 shells per kill. Millworth's gun crews were exhausted but exhilarated, experiencing the satisfaction that came from accomplishing their mission with unprecedented effectiveness. Sergeant McKinley was supervising the replenishment of ammunition when he noticed something that would have been invisible to anyone without extensive artillery experience. The gun barrels were significantly cooler than they should have been after hours of sustained firing. Conventional anti-aircraft engagement required sustained fire that heated gun barrels to temperatures that required careful management to prevent warping or damage. The reduced ammunition expenditure made possible by VT fuses meant that guns could engage more targets while firing fewer total rounds, dramatically extending the sustainable rate of operations. The tactical advantages extended beyond simple hit rate improvements. Gun crews that were not exhausted from sustained high-volume fire could maintain alertness and effectiveness throughout extended engagements. Ammunition supplies that lasted longer meant fewer supply convoys vulnerable to air attack or mechanical breakdown. Most critically, the psychological effect on gun crews of actually hitting their targets consistently could not be overstated. Soldiers who saw their fire achieving results maintained morale and effectiveness far better than those who fired thousands of rounds with minimal impact. At RAF Dymchurch, Malcolm Hendricks received the first combat effectiveness reports with a sense of vindication that 3 years of intensive development work had finally justified. The numbers were better than even the most optimistic laboratory predictions. Hit rates approaching 90% exceeded what controlled testing had achieved, possibly because combat conditions motivated gun crews to maximum precision. Hendricks immediately began drafting technical reports that would be forwarded to development teams in the United States, where engineers would analyze the data to refine future production. The security implications of the combat debut were immediately apparent. German forces would certainly attempt to recover unexploded VT-fused shells for analysis. Recovery teams were already being organized to search areas where shells had fallen, with orders to secure any fragments before German intelligence could examine them. The race to protect the technology while exploiting its tactical advantages had begun the moment the first VT-fused shell was fired in combat. Lieutenant Commander Faulkner at Dover Coast Command was compiling engagement statistics that would eventually be incorporated into official histories of the air defense campaign.
By 1300 hours on August 28th, anti-aircraft batteries under his command had engaged 97 V-1s and achieved 88 confirmed kills. The 9 flying bombs that penetrated the defensive belt had all been damaged by near misses, causing 7 to crash short of London and 2 to detonate in outlying suburbs with minimal casualties. For the first time since the V-weapon campaign began, a full day of German launch operations had achieved essentially zero strategic effect. The human cost of this technological triumph was measured in lives saved rather than casualties inflicted. Civilian defense officials estimated that the 88 V-1s destroyed would have killed or seriously injured between 1,500 and 2,000 people if they had reached their intended targets in London. The VT fuse had just saved more British civilians in a single morning than any other defensive technology introduced during the entire war. The implications for morale, industrial production, and political stability were profound and immediate. Dr. Ziegler at Johns Hopkins received a coded telegram that afternoon containing a single word: magnificent.
The development team that had spent 3 years perfecting proximity-fused technology finally had confirmation that their work had achieved its intended purpose under actual combat conditions. The celebration was muted by security restrictions that prevented public acknowledgement, but the satisfaction of seeing theoretical physics translated into practical life-saving technology was reward enough for scientists who had dedicated years to this single, focused objective. At Luftwaffe headquarters in Berlin, the situation reports from France were creating panic among officers who understood the strategic implications. The V-weapon campaign had been presented to Hitler as a potential war-winning technology that would compensate for setbacks on the Eastern Front and in France. The sudden collapse of V-1 effectiveness threatened to expose German claims about advanced weapons as hollow propaganda. More critically, the resources invested in V-weapon production represented manufacturing capacity that could have produced conventional aircraft, tanks, or artillery that were desperately needed to defend against Allied advances on multiple fronts. The technological gap between German and Allied capabilities was becoming undeniable to officers who had previously believed Nazi propaganda about inherent Aryan superiority. If the Allies could develop and deploy a defensive technology that rendered German weapons ineffective, what did that reveal about relative industrial and scientific capabilities? The V-1 campaign's failure was more than a tactical setback. It was evidence that Germany was losing the technological arms race that would ultimately determine the war's outcome. As evening approached over southeastern England, the day's final statistics revealed the magnitude of what had occurred. German forces had launched 126 V-1s in their most ambitious single-day operation of the entire campaign. British and American anti-aircraft batteries equipped with VT Fuzes had destroyed 115 of them. Fighter aircraft had accounted for an additional 6 kills. The 5 V-1s that reached London caused 27 casualties, the lowest total for any day with comparable launch numbers since the campaign began. The transformation in civilian morale was immediate and palpable. Londoners who had spent 2.5 months living under constant threat of random death suddenly found that threat reduced by more than 90%. The psychological relief was as significant as the reduction in physical danger. People could sleep without constant fear of being awakened by that terrible buzzing sound overhead. Children could play outside without adults scanning the skies every few minutes. Normal life, suspended since mid-June, suddenly seemed possible again. The strategic implications extended far beyond the immediate tactical success. The VT Fuse had demonstrated that technological innovation could fundamentally alter the balance of military capabilities in ways that numerical superiority could not overcome. German forces could launch 1,000 V-1s and achieve nothing if defensive technology destroyed them all before they reached their targets. The lesson that technology and industrial capacity mattered more than courage or numerical strength was being learned by both sides, though with very different emotional reactions to that lesson. Captain Millworth assembled his gun crews that evening for a brief address that captured the significance of what they had accomplished. They had participated in a technological revolution in warfare, proving that proximity-fused ammunition could transform anti-aircraft defense from an art of probability into something approaching scientific certainty. More importantly, they had saved lives, fulfilling the fundamental purpose of defensive operations. The satisfaction visible on the faces of exhausted gun crews reflected not just professional success, but moral accomplishment. They had done good work that day, and they knew it. As darkness fell over the channel, observation posts reported that no V-1 launches had occurred since early afternoon. German commanders apparently recognized the futility of continuing operations in the face of defensive capabilities they did not understand and could not counter. The saturation attack that was supposed to overwhelm British defenses had instead revealed a technological gap that made continued V-weapon operations strategically pointless. The vengeance weapons that had terrorized civilians for 2.5 months had encountered a defense they could not penetrate, and the balance of the air war had shifted decisively in favor of those defending their homes against mechanical terror.